Assalamu alaikum everyone. So lecture number 8, and today we will be going through the last chapter which we have finished, and the title of the chapter is Transmission Fundamentals, and we will be solving different questions in order to have a recap of this chapter. So these are the bullets which we will be touching in order to solve the questions, and in that way we will be having a recap of the underlying chapter. So first, the relationship between frequency and period. Then as we all know that we can represent each signal by sinusoids, so representation of a signal by using sinusoids. And then we also have a very renowned relationship between frequency and wavelength, so we will be solving some of the questions by using that relationship. And then when we represent a signal with the help of different sinusoids, so those sinusoids, they actually have different frequencies, different wavelengths and different phases. So how we are going to calculate the amplitude, frequency and phase in case of a signal that is represented by sinusoids. Then as we can decompose a signal into different frequency components, and how we decompose, and we will be solving different questions by decomposing a signal into its different components. Then in case of a signal that is being represented by a sinusoid, so how we are going to measure the period of that signal that is being represented by sinusoids, right? So sinusoidal signal period. Then after that we will be going through the periodicity if we have a linear combination of two periodic signals. So how we will be resolving the or computing the periodicity or mentioning the periodicity. So normally when we decompose a signal into different frequency components, we have the components with different frequencies. For example, if F is the fundamental frequency, then we can have different components that are actually integer multiple of the fundamental frequency, that is F, right? So normally what we do, we take the first few harmonics and ignore the rest of the harmonics, as most of the energy of the signal is contained within those few first harmonics. So what are the effects if we ignore the higher order harmonics, or on the other side if we ignore the lower order harmonics, right? Then how we compute the channel capacity, and we have very renowned formulas, Shannon formula and Nyquist criterion. And then finally we will be discussing about solving problem related to signal to noise ratio. So let's start. So here we have a question that the fundamental frequency of the signal is 1000 Hertz. So what is its period? So here I have mentioned a note that in order to have the Fourier analysis, what we need to do, we need to represent a signal as a combination of sine with different frequencies and amplitudes and phases. So all the components, they will be having different frequency, amplitudes and phases. So as this is the same, we already have gone through that all these signals, they actually are made up of different frequencies. For example, a square wave, so we can decompose a square wave into its different frequency components, so they will be having different frequency, or you can say integer multiple of the fundamental frequency. Okay, so here I have shown it graphically, so you can see that at the top we have a sine wave with frequency 2f, or here in the middle we have a sine wave with frequency 3f, and here we have superimposed those two frequency components. So actually the frequency over here is f and this is 3f, so you can see one vibration is being made in 1 second, so here 1 and a half, so 3 vibrations are being made in 1 second, so 3f. So after superimposing, so we will be having the outcome like this. So you can approximate this curve which is at the bottom with the square wave. So if I approximate it, so you can see we can approximate this as a square wave. And this is the relationship between frequency and time period. So let me mention again that if one vibration is being made in 1 second, so actually instead of 1, so let's say f vibrations are being made in 1 second and 1 vibration has to be made in 1/f second, and that is actually the time period. So this is the relationship between t and f. Right, so here we have the relationship frequency is equal to 1/time period or 1/t, and it is mentioned in hertz, units are in hertz, or we have time period is equal to 1/f, and this is in seconds. So here we have the answer, period is equal to 1/1000, so 0.001 second or 1 millisecond. Okay, so here what we have to do, we have to, you can see we have sinusoids, different sines with different frequencies and different phases. So we have to simplify this in order to represent those sinusoids. So here we have two sines that are being added, right? So we can use this formula, right? So let me call this x, and this is actually y. So here we have, or you can call it u, and here we have v. So u plus v over 2. So 2 sine 2 pi ft minus pi plus 2 pi ft plus pi, and then we will having, this is cos, that is multiplied by 2 pi f t minus pi, and then minus 2 pi ft and minus pi. So this will cancel with this, and here this will be cancelled with this. So it means we have minus 2 pi. And for sine we are having, so we forgot to mention 2 divided by 2 divided by 2. So sine 4 pi ft divided by 2, and here divided by 2, right? So as we know that in case of cos, the sine inside the argument or inside the angle is absorbed. So we will be having 2 sine 4 pi ft, or rather 2, because 2 will be cancelled with this 4. So here we have minus and cos of pi. So that is equal to 1. As if we compare sine and cosine, so sine actually starts from 0 and cos starts here. So this is 90 and pi. So at pi, cos is maximum, but on the negative side, so that's why we have a negative sign over here. So we will be having minus 2. So here plus, because we have not solved it, 2 sine 2 pi f of t. So that is the simplest representation we can have. So next for this, okay, so again you can say this is alpha and here we have beta, because now the notations has been changed. So sine of 2 pi ft and cos of sine of alpha and cos of 2 pi ft minus pi plus sine of beta, it means 2 pi ft minus pi into cos of alpha, so 2 pi ft. So this expression will be 0 as a result of this, and here sine of 2 pi f will be 0, so we will be having 0 as a resultant. So that's it. So we have expressed in their simplest form or solved them. So here we have frequency wavelength relationship questions. So the question is, sound wave may be modeled by sinusoids. So we compare the wavelength and the relative frequency of musical notes, and here we have given 330 meter per second, and that is the speed of sound. And here we have also the frequencies of different notes. For example, note C 264, D 296, 7, and here we have E330. So a difference of 33 for each note, right? So you can see the wavelength, the distance between two successive points on a wave. So you can say this is crest and here we have trough, so between two crests. And here if you mention the points, so distance between two points onto the wave, similar points, right? So this is the wavelength. So we have already have the relationship, that is T is equal to 1 over F, or F is equal to 1 over T. That is the relationship between time and frequency. And now let me use this formula, S is equal to Vt, where S is the distance and V is the velocity and T is the time. So in case of different waves, or when we are dealing with different signals, so here S will be lambda, that is the distance between two successive crests or troughs, or distance between two similar points on a periodic wave. And then we have velocity, V, velocity of the signal being used, and then we have the time period instead of time, that is T. So let me write down the equivalent equation for S is equal to Vt. So as mentioned, S is lambda, V is the velocity, and T is the time period. So if I replace T is equal to 1 over F in this equation, right? So lambda is equal to V over F, and we will be having lambda F is equal to V. So this is the relationship between wavelength, frequency, and velocity. So that's what is required in order to solve this question. So question is given, right? So what we need to do, we need to put the values. So we know the V, that is 330 meter per second, and we have F, that is 264 for C. So let me write down, it's hertz, and that is F for note C. So as we know, lambda F is equal to V, and lambda is equal to V over F. 330 divided by 264, right? So that will become 1.25. So that is in meter, right? So in similar way we can solve for rest of the nodes, right? So you can see for D we have 297. So we can see, because these are the nodes, and we can use the velocity of sound 330, that will remain constant for all the notes. So 330 by 297, and then 330 by 330, right? And then we have 0.93, and then you can see that the wavelength is reducing as we are having high frequencies. So this is the table mentioning the wavelength for different notes, and here we have the difference. So 33, 33, and here we have a difference of 22, 44, 44. So these are the differences between consecutive or neighboring notes. N for note, F for frequency, and D difference in the frequency, and W is mentioning the wavelength in this table. Okay, so here as we all know that whenever we are going to represent a signal with different frequency components, so those components, they might be having different amplitude, different frequency, and different phase. So here we have a question. So we are given two curves in this figure. One is a solid line curve and other is the dotted line curve. So what does the dotted curve represent? So solid line curve is represented by sine 2 pi t. So you can see from the expression that it's a sinusoid, and can be written if we have to represent this dotted line in terms of this solid line. So in that case, well, what will be the amplitude, frequency, and phase? So first we need to know amplitude, frequency, and phase. So here you can see we have a sinusoid, sine wave. This is the time period, and here we have the amplitude. So this is the amplitude, maximum amplitude. So here we have a change in the amplitude. So change in frequency and change in phase, 0 degree, 90 degree, and here we have pi, phase change of pi. So you can see that this dotted line, it has an amplitude of 2 sine 4 pi t plus pi. So if I start from here, so you can see if I have to compare the phase of this solid line and the dotted line, so this is actually starting from 0 right away, and here we have a phase difference of pi. So that's why we have pi over here, and this is the amplitude of this dotted line, and frequency is 2. So how you can see that this is the time, and for this dotted line, one vibration is being made in an amount of time 0.5 seconds. So if I have to calculate the frequency, and I know that f is equal to 1 over t, so 1 over 0.5, 10 by 5, and we will be getting 2. So this is the time period. So you can this is the frequency. So phi t, so pi is the phase, and frequency is 2, and amplitude is 2. Okay, so now we have to decompose a signal. So this is the given signal, and we have to decompose this signal into a linear combination of sinusoidal function, and after that you need to find out the amplitude, frequency and phase of each component. So first of all, we need to simplify by using different trigonometric identities. So as you can see that we have two coses, two cosinusides. One is cos 5t and here we have cos 100t. So first we will be multiplying. So this is the bracket cos 100t, when we will multiply this with this one, and then plus 0.1 cos 5t and cos 100t. So now we will be using this trigonometric identity, that cos A and cos B. So I'm solving this. Cos 5t and cos 100t. So 1 by 2 cos A plus B plus cos A minus B. So cos 100t, this is the same. For this 1 by 2, so we have already 0.1, so 0.1 divided by 1 by 2, so 0.05, and when we will be having 5t plus 100t. So first expression add up the angle, so 105t, and then we have to take the difference. So I'm taking this as A and this as B in order to avoid the negative sign, but it will not make any difference because the sine will be absorbed by the cosinusoid. So A minus B, so 95, 100 minus 5, 95. So by using this identity, we have decomposed this signal into cosines. Cos of 100t plus 0.05 cos 105t and 0.05 cos of 95t. So if I arrange, so 0.05 cos of 95, so here there should be t, plus, so let me write here because there is some problem in 0.05 cos of 95t, and then we have cos of 100t, and after that I will be having 0.05 cos of 105t. So you can see 95t, 100t and 105t. So this is the arrangement. So here comes the sinusoidal signal period. So how we will be calculating the period of a signal that is represented by sinusoids. So the signal is f of t is equal to 100 cos t and whole square. So we have to use trigonometric identity in order to simplify this expression. So cos square t, so we can decompose cos x, and as we know cos A, cos B, that is the last cos A, cos B. Okay, 1 by 2, first addition and then subtraction of those angles. So 1 by 2 cos 2x plus 1 cos 0 is 1. So in case of this, what we need to do, we need to square of 10 is 100 and we have cos square t, or that is equal to cos t into cos t, right? So we'll be having 1 by 2 and that will be 100 divided by 2 cos 2t plus 1, that is equal to 50 plus 50 cos 2t. So how we will be evaluating the period? So we will be having cos 2t, and how we will be calculating the period of f of t. So if we talk about the cosinusoid, so we are having cos of 2t. So let me write down, because we know that I can write this as 2t plus 2 pi n, where n is an integer. So let me 2a is equal to, remember that n is an integer, so that's a is equal to pi n, and again n is an integer, it can take on any integer value, so we are left with period is equal to pi, right? So it means this as a result of this cosinusoid that is present over here, the period of the signal f of t will be pi, right? So that is the way out of finding the period of a sinusoidal signal. So now comes the periodicity. If we have a signal that is actually composed of two signals, so it is a linear combination of two signals. So question is, we have two periodic signals, first one is f1t and second one is f2t, and the corresponding periods of those two signals are t1 and t2 respectively. So we can write if ft is a linear combination of f1t plus f2t. So how we can demonstrate that their linear combination is also periodic, and if it is not periodic, so what are the conditions that has to be mentioned that this is not periodic? So first of all, periodic signal, we all know that the signal that repeats itself after a predetermined amount of time is called a periodic signal. So if in case of mathematical notation, we can represent a periodic signal in this way: s of t plus capital T, where t is the period, is equal to s of t. So here you can see signal is repeating after this much amount of time. So for this sinusoid, this is square wave. So you can see the effect. So here we have a signal with frequency f, and here we have signal with frequency 3f, and those signals are superimposed, and we are having this, right? Okay. So here is the solution, but we have theoretical justification. So we know that if, let's assume that period of f1t is x, so we can write f1t is equal to f1t plus x, and n is an integer, and x is the smallest value, such that f1t is equal to f1t plus x. And similarly we can do this for second signal, and here we are using y to have some sort of differentiation. f2t plus my, where m is the smallest possible value. So whenever we will be having a linear combination, or we are adding those signals, so then the period will be z. So you can say f of t is equal to f of t plus z. So this is a very good example that here we have. This is you can say f1 with period frequency f, so this implies t, and here we have frequency, so you can see f2t, frequency 3f, so this implies f is equal to 1 over t, so 3f, so it means period will be reduced. So you can see that it's 1 by third of t. That is the fundamental time period, or this is the fundamental frequency, right? So if I take this, right, so you can see that this is superimposed over here. So the highest frequency, that is 3f, so let me 1 and 1.5, so 1 and 1.5, so 3f, right? So 3f is superimposed here, but we will be having a different period, right? So here and 1. Okay, so the last equation, that is this one, f of t plus z, f2t plus z, f1 is equal to ft plus z, and f2t is equal to t plus z. So let's z is equal to nx is equal to my. So it means n over m y over x. So if the ratio y over x, or you can say n over m, is a rational number, then we can say that the signal that is actually composed of the linear combination of f1 and f2 will be a periodic signal. So this is the condition, that the ratio should be rational. So here we have another question that is relevant to signal harmonics. So as we know that any signal can be decomposed into different frequencies, and those frequency components, they are actually called harmonics, right? And normally what we do when we decompose a signal into its harmonic components, we take first few harmonics, and the reason for ignoring the rest of the harmonics is that the most of the energy that is contained within the signal, that is represented by different frequency components, is contained in the first few harmonics, first few frequency components, and that's why we can ignore the higher order harmonics, right? So there can be another case where we ignore the first few harmonics that are the lower order harmonics, and we consider the higher order harmonics. For example, if I have a signal and I decompose that signal into different frequency components, f1, 3f, 5f, 7f, and 9f, and so on and so forth. So normally what I will do, I will take the fundamental frequency, that is f, then its first three harmonics, 3f, 5f, and 7f, because most of the energy is contained within those lower order harmonics, right? So let's function that is x of t, right? So I am decomposing that into x1, x2, 3ft, x3, 5ft, plus x4, 7f, that is 7ft, and so on and so forth. So what I normally do, I 1, 2, 3, 4, I will take those 4 lower order harmonics, and I will ignore the rest of the harmonics because most of the energy is contained within those frequency components. But there can be the reverse of that, that I will be ignoring all those lower order harmonics, and I will be considering or representing the, for example, x5, and that is 9ft plus x6, 11ft, and so on and so forth. So what will be the impact of that? So as a result of this, when we reverse, that we are ignoring the lower order harmonics and we are considering the higher order harmonics, the signal would be carrying lower amplitude and the waveforms will be changing rapidly. So that will be the elimination of lower order harmonics that contain most of the energy. So here comes the channel capacity. So how we are going to compute the channel capacity. So here we have a question: what is the channel capacity for a teleprinter channel with a 300 Hz bandwidth and a signal to noise ratio of 3 dB? So first we need to know the channel capacity, maximum possible data rate on a communication path, and here we have some of the bottlenecks: data rate in bits per second, bandwidth in cycles per second, in noise. That is one of the major bottleneck to achieve the maximum channel capacity, and error rate, that the number of bits that are being corrupted. So these are all the limitation factors, right? And the reasons for those different bottlenecks, they are physical properties of the channel. Okay, so here we have the Shannon formula in order to achieve the maximum data rate, but one point here is very important to mention, that whenever Shannon was discovering his formula, he has taken into account only one type of noise, that is the thermal noise, and we normally model this with Gaussian. We call it a Gaussian noise. So here is the Shannon formula. We already have gone through this, that the capacity of a channel is B log base 2 1 plus SNR, where SNR is signal to noise ratio. right? MB is the bandwidth, C is the capacity, and so here we have the question, and we are given the bandwidth W is equal to 300 Hertz, SNR, right? So that is actually 3. SNR is equal to 100 raised to power 0.3. So we have to replace the values over here. So B bandwidth 300 Hertz, and this is the signal to noise ratio of 3 dB, right? So, and after calculation we got the channel capacity, that is 474 bits per second. So if we are given data rate and we want to compute or calculate the bandwidth, so a digital signaling system is required to operate at 9600 bits per second. So this is given, data rate is given. So the question is, encodes a 4-bit word, what is the minimum required bandwidth? So this is signal levels 4-bit, and if we have 8-bit word, so we have two formulas actually in order to relate the data rate and the bandwidth. First one is Nyquist, and in order to apply this formula we have to assume that the channel is noise free, which is not the case. We always will be having noise whenever we will be transmitting a signal via channel. Then on the other side, if we talk about the Shannon formula, it assumes only the Gaussian noise, that is white noise. Okay, so signals with more than 2 levels can be used, that each single element can represent more than 1 bit. For example, here 4 different levels, 00, 01, 10 and 11, right? So here is the Nyquist criterion. C is the channel capacity, B is the bandwidth, and M are the number of discrete signal levels, right? Okay, so this is the question. So we are given the bandwidth, C or channel capacity 9600 bits per second, that is the data rate, not the bandwidth. Bandwidth we have to find. So M is 4 in the first case, 4-bit word. So we will be placing values in the Nyquist criterion formula. C 9600 to B into 4, so B is 1200 Hertz, that is the bandwidth. So in the second case, when we have 8-bit word, right, so M is equal to 8 here, 2B into 8, so we will be having 600 Hertz. So you can see that the bandwidth has been reduced. So we have another question from the Shannon and Nyquist channel capacity, upper limit on the bit rate of a channel based on 2 different approaches. So how we can relate them, right? So you can see that we have Shannon formula, C is equal to B1 plus SNR, and so in case of Nyquist criterion, we assume that the channel is noise free, so signaling rate is limited by the channel bandwidth, while on the other side Shannon focused on signaling rate that can be achieved over a channel with a given bandwidth, given signal power and in the presence of noise, but remember only the white noise, Gaussian noise. So here we have to discuss the theoretical and the actual channel capacity, right? The reason for this is that in the first case, when we talk about the Nyquist criterion, the channel is considered an ideal channel, that is noise free, which is not the case whenever we talk about the practical channel like fiber optics or copper cable or coaxial cable, or you can say the in case of wireless we have free space. So they all are noisy channels, so they should be a theoretical and actual channel capacity discussion. And there are some codes like turbo codes that are very close to the Shannon limit, because they are actually using the feedback of different interlevers, right? So here we have the question, narrow audio bandwidth of a telephone transmission facility, a nominal SNR of 56 dB and a distortion level of 0.2, less than 0.2%. So what is so what is the maximum channel capacity, that is in the context of theory, and what is the actual channel capacity? So here are some of the definitions which we have already gone through. So if you look at the Shannon formula, C is equal to B log base 2 1 plus SNR, so that is 56 kilobits per second. So there is a distortion level, right, as well as other impacts on the capacity. The actual maximum will be somewhat degraded from the theoretical maximum, right? So there should be a difference. So here comes the signal to noise ratio. So we are given a channel with an intended capacity of 20 megabits per second. The bandwidth of the channel is 3 megahertz. So we need to calculate the signal to noise ratio in order to attain this capacity. So as we know that noise is an unwanted signal, so we have different sorts of noise, so that we don't need to discuss. So in order to have or achieve the signal, the noise level should be less than the actual signal level, right? So we actually here will be putting the values. Channel capacity 3 megahertz, so 3 into 10 raised to power 6, and capacity is 20 megabit per second. 20 into 10 raised to power 6 megabit log base 2 1 plus SNR. So SNR is equal to 101. So this SNR should be achieved in order to is required in order to achieve this capacity, that is the 20 megabit per second, and the bandwidth is 3 megahertz. Okay, so that's all, and here we have finished the recap of the chapter Transmission Fundamentals, and we are actually today we have discussed different topics, different terminologies, different techniques in via solving different questions. So let me conclude. So first we discussed you can see period relationship, then we talked about the representation of a signal by different sinusoids, and then we talked about frequency wavelength relationship. So whenever we have to represent a signal in the form of different frequency components, those frequency components, they actually carry different amplitude, different time period, different frequency, and different phases. So how we actually relate them and how we are calculating those different parameters. And then the decomposition of a signal into its sub-components, or you can see harmonics. So in case of sinusoidal signals, so how to measure the time period. So, and then if we have two different signals that are periodic, and we have mentioned the linear combination of those two different periodic signals as another signal, or as a so the resultant is another signal. So we discussed about the periodicity of the resultant, and then whenever we represent a signal with different frequency components, those frequency components, they are actually called harmonics. So normally what we do, we take first few harmonics that actually contain the most of the energy of the signal and ignore the rest of the signal because they are carrying very low energy, and that can be ignored. So in another case, if we ignore the lower order frequency components and we consider the higher order frequency components, so what will be the impact? So that we have discussed. Then how we compute the channel capacity, and we have used Shannon formula and Nyquist criterion in order to solve different problems. And finally we discussed about signal to noise ratio. So that's all. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफिज़. अस्सलाम वालेकुम.